Okay, so we're just going to work through a set of problems relating to the content of fundamental principles in the unit Foundations of Physics for PHYS1006. So this is our week 1, 2 and 3 content. So here we've just got some theory, example, and then we're just going to work through the questions. So how many significant figures are in each of the following numbers? We're just going to use this definition of significant figures here. So by using that, we can see that A has 3 significant figures, B has 4 significant figures, C has 2 significant figures, and D has 4 significant figures. The reason why B has only 2 is because these are our only significant figures. Leading zeros are insignificant, however trailing zeros are significant. So this here is 4 significant figures. Now we're going to write these numbers in powers of 10 notation. So what that means is that powers of 10 notation, it can be any number times 10 to the n, where a is any number, n is any integer, positive integer, or any integer really. So this here, I'm just going to do it, say, in the form a, where a times 10 to the b, where a is less than 10 and greater than 0. So decimal numbers that are 1 digit. So the first one, a is 1.156 times 10 to the 0. The reason why we do 10 to the 0 is because anything, say, x to the 0th power is going to be equal to 1 for every value x. So to keep this consistent with the significant figures, let's write this in 2 significant figures. So this will become 1 times 10 to the 0. Now this one in 2 significant figures is a 6.8 times 10 to the 1, 2, 3. So we need a factor of 10 to the minus 3 to bring this number to be equivalent to this here. So we're getting this decimal here, or we're imagining that the decimal is right in between the 6 and the 8, and we're going to add a factor of 10 to the minus 3, which brings the decimal back 3 places, thus giving us this number. Now we will do the same thing for C, where we have 3.3 times 10 to the 1 and 2, and then in the exact same way we do it for D, times 10 to the 2. Convert the following measurements to full decimal numbers without prefixes. So this question asks us to test our knowledge on prefixes of units. So here we can just use this table, which is given in almost every formula sheet, so you don't have to remember it, but as you do more physics, it just becomes remembered. So we start with A as being 286.6 millimeters. Now what we know is that 286.6 millimeters. What we know is that there is 10 10 to the minus 1, so there are 10 millimeters in a centimeter, so going from millimeters to centimeters means that we're dividing it by 10, and then we have to do it another 10 to the minus 2, so that's 10 to the, so that just means that there is 100 centimeters in a meter. So what this does is this factor converts it from millimeters into meters. So by index rules, because we have the same base, the indices just add up, and this just becomes 10 to the minus 1 minus 2, which is 10 to the minus 3. So this answer is just 286 times 10 to the minus 3. But if we were to express this number into significant figures, we would need something like 2.9 times 10, but because we are expressing with a decimal all the way here, or what we can do is maybe more sensible to just do 29 times 10 to the minus 4 meters. So, or you can do 0.00029, 1, 2, 3, 4. So this is maybe what it's asking us to do, full decimal numbers. So I'm guessing maybe that. So B, we have 760 milligrams. So milli is 10 to the minus 3. So all we have to do is do this, 10 to the minus 3, and then we have grams, and we know that there is 1,000 grams in a kilogram, so we just do another 10 to the minus 3, so then this becomes 760 times 10 to the minus 6, so then we have to do 0.00000, 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6. So kilograms. Now C, we have 22.5 nanometers. So 25.2 nanometers. Nano is 10 to the minus 9. Oops. What did I just do? I don't know. Okay. So nano is 10 to the minus 9 right here. So this is just 10 to the minus 9. And this will be pretty long. 1, 2, 3, 4, 5, 6, 7, 8, 9, 5. So 1, 2, 3, 4, 5, 6, 7, 8, 9 meters. And then D, 2.5 gigavolts. So we go and look at what giga is. Giga is 10 to the 9. So this is just times 10 to the 9 volts, which is 5. So that will be 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So I did one too many zeros. So this will be, what is this? So that's there. So there's a 3 there, 3 there, and 3 there. So 2.5 billion, I think. Yes, because that's 500 million. So volts. Using appropriate prefixes, express the following quantities. So this is just going to do the opposite of what we just did. So 0.0056 meters. So 1, 2, 3, 4. So it's probably better to do in a 3 or a 6. So we can go 1, 2, 3. So 0.56 times 0.56 times 10 to the minus 3 meters times 10 to the minus 3 is milli, so we can just write 0.56 millimeters here. So that's A. B is 1250 seconds. So 1250, you can do 10 to the 3 again. So this can just be 12.5 times 10, sorry, 1.25 times 10 to the 3 kiloseconds. Now, if we were to express this in two significant figures, this would simply just be 1.3 times 10 to the 3 kiloseconds. Now C, we have this here, so 1, 2, 3, 4, 5, 6. So micro corresponds to -6, so we have 8.3 microkilograms. D, we have 7.5 million volts, so this is 1, 2, 3, 4, 5, 6. Times 10 to 6 is mega, so this is just 7.5 megavolts. Okay, a typical atom has, a diameter of 1 times 10 to the minus 10 meters. Approximately how many atoms are along a 1 centimeter line? So 1 centimeter is equal to 0.01 meters, which is equal to 1 times 10 to the minus 2 meters, because 1 and 2. So essentially, we are just going to see how many times this number goes into this number. So then our number of atoms is equal to 1 times 10 to the minus 2 over 1 times 10 to the minus 10 by index rules. These are just, 1 times anything is just that, so you can just think of it as 10 to the minus 2 over 10 to the minus 10. It doesn't really matter, you can write it anyway, but 10 to the minus 2 minus 10, minus 10, because if it's in the denominator, then so this is another index rule here. If you've got a to the n over a to the m, this is equal to a to the n minus m, and the other one is a to the n, a to the m is equal to a to the n plus m. So then this is equal to 1 times 10, so this just becomes plus minus 2 plus 10 times 10 to the 8 atoms, or 10 1, 2, 3, or you can, it's 100 million atoms. Okay. Car travels at 100. So car travels at 160 kilometers per hour. Dropped at this height. How many seconds before being directly overhead should the package be released? So the scenario that we're dealing with is, so this should be a plane, just because it's easier to see. So we've got a plane here, and this is going to be flying with a speed 160 kilometers per hour. So, and then we have this plane is going to be 160 meters in the air, and this is where we want to drop the package. So at what time before we're directly above the package should we drop it? In other words, we want to find how long it takes for the package to hit the ground, and if we find that time, then we know the how much time we should have in between dropping the package and being directly over the drop-off point. So we are going to need a time as our unknown. Our A is going to be minus 9.8 meters per second squared, the gravity present on the surface of the Earth. And we're going to have that the plane travels at this speed. However, we're not really concerned with how fast it is going, because all we want to find is the time it takes for the package to fall down. For this displacement, we say x. We say the displacement of 160 meters. So we need an equation that relates TAX. So let's go up to our kinematics equation and see which one would work. So this has a time, a displacement, an acceleration, and I think that this will work. So let's just write this down. XF is equal to xi plus vit plus 1/2 at squared. And then let's go and bring this down here. So then we have that our xf will be 0 because we're considering that this equation is relating to the motion of the package, not the plane. So this is our package and it's going to fall along this path. So our final displacement of the package we say is 0 because we're going to measure up as being the positive. So we can imagine that this scenario is graphed on this xy plane here, where this is our origin and this is our x and this is our y, where this is going in the positive directions. So 0 is our final displacement. Our initial displacement would be 160 because, as you can see here, we're going to be starting up here and the package is going to fall down to the origin. So 0 is equal to 160 plus our initial velocity. Well, our package will have an initial velocity of 0 because it's not moving. So 0t plus 1/2 a is minus 9.8 t squared. So we can move this 160 over to the other side, maybe another color. So this can go over to this side and the sign changes. So this becomes minus 160. This is just 0 is equal to 1/2 of minus 9.8 t squared. So what we can do is we can times both sides by 2 and then divide it by this 9.8. So then we get 160 times 2 is 320, so minus 320 over 9.8 minus is equal to t squared. But what we can do is notice that this minuses cancel and then we square root both sides. This square root cancels with the square, so then what we get is t is equal to square root of 320 over 9.8, which we find to be square root of 320 over 9.8, 5.71, so 5.7. So because we're in 3 significant figures, we will do 5.71. 5.71 seconds. Okay, the sun is on average 93 million miles from Earth. Convert this distance into meters using powers of 10, kilometers using a metric prefix. So 1 mile is 1.6 kilometers. So to get this value into kilometers, we do 93 times 10 to 6, because we could look here and we see that a million corresponds to a mega, which is 10 to the 6. We need to get this and we times it by 1.6, because there is we need to actually divide it by 1.6. So this is a mile equals 1.6 kilometers. If we divide both sides by 1.6, we get 1 kilometer is equal to miles divided by 1.6. So that's just converting the values. So let's do this in a calculator. 93 times 10 to the 6 over 1.6 is 58 million. So 58 times 10 to the 6. 58 times 10 to the 6 meters. Right. No. This is kilometers. So then, because there's 1,000 meters in a kilometer, this becomes 58 times 10 to the 6 times 10 to the 3 meters, because by the index rules again, these add, so this just becomes 10 to the 9 meters. And then B, so this is kilometers, so with a prefix, this just becomes 58 megakilometers. A circle has a radius of this. Calculate the area of the circle and its approximate uncertainty. So we're going to have to use this formula for uncertainties. So our formula will be area of a circle, which is pi r squared. Pi is just a constant, r is a variable that we're after. So the uncertainty of A, or I should say the fractional uncertainty of A, will be equal to 2 times the fractional uncertainty of R. So let's just bring this formula down with us. So this can go here. Put that over here so we have some space. Okay. So first we'll calculate the area without the uncertainties. So A will be equal to pi times 1.57 squared. So just chuck that in a calculator. 1.57 squared times pi, which is 7.74 meters squared, and then we will find, well, from this formula here we can get that delta A is equal to A times 2 delta R on R. So then we find that delta A is equal to this value here, so 7.74 times 2 of 0.05 over 1.57, which we just put into a calculator. So what we can do is just bring this here. 7.74 times 2 times 0.05 over 1.57, which is 0.49. So this is 0.49. Thus, A is equal to 7.74 plus or minus 0.49 meters squared. Okay. Determine how many acres are in 1 hectare, given that 1 hectare is defined as 10,000 meters squared and 1 acre is 4,047 meters squared. So 1 hectare is 10,000 meters squared. And 1 acre is 4,047 meters squared. So how many acres are in 1 hectare or hectare? You would just divide this by 447 meters squared, and this will give our number. So how many acres are in 1 hectare? Because you just divide this value by this one, and you get 10,000 over 4047. So 10, 1, 2, 3 over 4047. That gives you 2.47. But because this is in 4 significant figures, this will be 2.471. So equals 2.471 acres per hectare. A light year is the distance light travels in 1 year at this speed. How many meters are in 1 light year? So meters will be equal to 3 times 10 to the 8. So this is going to be in a second. So this is the meters traveled by light in 1 second. So a light year is the distance light travels in 1 year. So because this is a second, we will need to times it by 60, because there's 60 seconds in a minute, and then 60 minutes in an hour, and then 24 hours in a day, and then 365 days in a year. So let's just bring our calculator back. So what do we have? 3 times 10 to the 8 times 60 squared times 24 times 365, and we get a number like this, and we are in 3 significant figures, so this is just 9.46. 9.46 times 10 to the 15 meters. Okay. How many astronomical units are there in 1 light year, if that is that? So 1 light year is that many meters. So we just do simple division times 10 to 15 over 1.5 times 10 to the 11. So 9.46 over 1.5. 10 to 15, 10 to 11. Well, 10 to 15, 10 to 11, you will be left with 10 to 4. So this is 6.31 times 10 to the 4. 0.31 times 10 to, it's pretty difficult. Yeah. We'll just move on to 12. So a light plane was reaching speed of 120 kilometers per hour for takeoff. How long runway is needed if the constant acceleration is 1.5 meters per second squared? So first, I just want to convert this into meters per second. So again, we have 1,000 meters per kilometer, and we have 60 times 60 seconds in an hour. So this is entirely equivalent to 120 kilometers per hour. I'm just changing the units. So you can start some calculator. 120 times 1,000 over 60 squared, we get 33.33 meters per second as our velocity. Now we want to find our displacement given an acceleration, so let's just look at our equations and find that this is the one that we're going to use because it does not have a t. So we have vf squared is equal to vi squared plus 2a xf minus xa, xf minus xi. So we can go and bring this down here. And then we're going to say that this is going to be our final velocity. Our initial velocity will be 0. Our initial displacement will be 0. Our final displacement is the variable that we're looking for, and I is 1.8 meters per second squared. The reason why I'm setting xi to be 0 and vi to be 0 is because I'm going to solve this problem under the assumption that this plane is starting from the origin, which makes sense because we are getting ready for takeoff. So we can substitute all these numbers in. We get 33.33 squared is equal to 0 plus 2 of 1.8 xf, because xf minus 0 is just xf. And then I can divide both sides by 2 of 1.8, which is 3.6. So 3.6, and then all of this goes away, and then we get this as being our value for xf. Now we can just put this into a calculator. We get 33.33 squared over 3.6, which is 308.58. And we are in two significant figures, so this is just 31 times 31 times 10 meters. Now, a baseball pitcher throws a baseball with a speed of 43 meters per second. Estimate the average acceleration of the ball during the throwing motion. Okay, so we have that. I think it's the exact same thing. Estimate the average acceleration. So we're going to use the same equation as before, this one here, and we're going to do the same assumptions that this ball is going to be starting from the origin, meaning vi is equal to 0, and xi is equal to 0. Now we have our xf as being 3.5, but now we're being asked to find a value for the acceleration. So what we can do is we can rearrange this by knowing that this is 0 and this is 0, meaning that our equation now is vf squared plus 2a xf. Now we can divide both sides by 2xf, and what we get is that this and this cancels with this, meaning that a is equal to vf squared onto xf. Now we can substitute our values in 43 squared because this is here, and then 2 times our final displacement 3.5, so 43 squared over 7, which is 264, so 226 times 10 meters per second squared, or 264 meters per second squared. Now, it doesn't really matter in terms of significant figures for numbers like this. Just leave it like that. Okay, and that's it.